Welcome to breadboarding. In the previous video we managed to get our 386 processor in its breadboard adapter here running a very simple 4-byte test program that we put in the dip switches here, and we managed to get some address output. Now in this video what we're going to start looking at doing is working out how we plug this chip into the rest of the computer, and we're going to be basing that on the Compaq DeskPro 386. So this is video 7 in the 386 Breadboard PC series, and in this video we're going to be looking at the 386 bus control, address, latches and the data buffers. These diagrams come from the internal design document that I referenced in the earlier videos, and I'll include the URL for it on archive.org in the description below. This first schematic actually shows the CPU, and the bits that we've already done in purple here, we've already done the clock circuit, the reset circuit and the CPU and the CPU adapter, but we still need to add a bit of logic here to handle the A20 address line handling to allow real mode applications to work with larger amounts of memory. So I'm just going to be quickly flying through the various screens here, identifying which bits we need to worry about and which bits we don't. This has got the bus control and the address latches, and you'll see here that this section here is only needed for use with DMA, so direct memory access. So we're not going to be looking at that for the moment. We'll leave that to later on in the series. We do need to worry about these latches and buffers for the address lines, these PLDs which are part of the control logic, another PLD that's part of the control logic. Then these are the data buffers. Now these data buffers here are only needed for DMA, so that DMA controller can talk to the 32-bit memory card. But we've got some more PLDs down here, another one here, and these buffers which are for the 32-bit data bus and converting that to the 16-bit ISA bus, and also for copying data between the lower 8 bits and the upper 8 bits, and also the buffer that goes off to all the system I/O devices on the X bus. So this is probably the more complex bit. In order for Compaq to get the best compatibility, rather than using the standard Intel bus controller chip like we used on the 286 and the 8088 PCs, they actually developed quite a complex state machine with a combination of this register here, which is configurable by the settings and things in this PLD here. There's quite a lot of complex logic here, but we don't really need to worry about that for now. Then the DMA we're going to be handling later on in the series, so I'm not going to worry about that quite yet. Now the interrupt controllers and the keyboard controller we will be looking at, but we don't need to worry about that for now, as the real-time clock and some of the additional decoding for the I/O devices and things. But we are going to need to worry about the ROMs here. So there's a PLD and the 2 ROM chips, and that's going to be used for doing our BIOS and also our Nanocomp monitor. The A20 speed-up extension that Compaq did, we don't need to worry about because the keyboard controller chip we're using is implemented in hardware, so it will be a lot faster than the original one used in the DeskPro. Then we also need to worry about the data bus buffering for the ROMs. Then at some point we'll look at the ISA bus connectors, so we can plug in a VGA ISA bus card. But then we also have to worry about the 32-bit memory expansion card. So in the original DeskPro, although it was compatible with 16-bit expansion cards, so things like VGA cards and things like that, the memory was handled on a dedicated connector so that it could actually work at 32 bits. So this was Compaq specific. This page shows the data bus side of things, and it was a little unusual in that these chips here, the 657s, is a bidirectional buffer but also has built-in parity checking. Now we are going to need to include the bidirectional buffers, but we're going to use a fairly standard LS245 bidirectional buffer that we've used on lots of the earlier projects. We're going to need to worry about this logic here, but the parity checking we're not going to bother with, so we don't really need to worry about parity checking for the Breadboard PC. Then we get to the address side of things. So these are the address latches which we're going to need to implement for the memory board, but some comparators here which are used as part of speeding up memory access for the dynamic RAM, which we don't need to really worry about. There's also another PLD here that we'll need to implement, another one here. These multiplexers for accessing the dynamic RAM we don't have to worry about. Then there's a bit of stuff here to handle the control registers which are used to control the memory board in particular, how to map the ROMs into high RAM, and also how to protect the RAM from being overwritten, and another PLD controller up there. And then there are lots and lots of these schematics for the memory cards. So if I just show you this one, so this is actually a row of chips which I think were soldered into the card, and then these were sockets, so they could be populated as time and money allowed afterwards. And you'll see here that on sheet number 5, we've actually got bits 0, 1 to 7, and then parity 0. And you'd then see on sheet 6, you would probably have bit 8 up to bit 15, parity 1. Sheet 7 would have bit 16 to 23 and P2, and then sheet 8 would then have bit 24 up to 31 with P3 for the parity. So you can see that having 32 bits of memory was quite a complex process before the introduction of sims and dims for handling memory. And then there's a couple of jumpers here to determine whether or not we've got a 2 megabyte or 8 megabytes of memory. And to start with, we're going to have 2 megabytes of memory with 4 512K chips. And finally, these are the mass coprocessors, the 287 and the 387. We're not going to worry about those. There are one or two places where we need to tie some control signals to high or to low voltages just to allow for that. So you'll notice through blasting through those schematics that there's a lot of programmable logic devices on there, and if just have a look at a little list of them. So this is a list of all of the PLD definitions that exist in the PDF document, and you can see here I've been tracking where I've been converting the PDF into the text format, and then as I convert them into the CUPL PLD language, and then when I convert the tests and the simulation for them. Now, the ones that we need to worry about actually for this stage in the project, there's 7 of them here. So these ones in orange, almost half of the PLDs are going to be needed to actually get this stage of the project working. So it's going to be quite complicated. Now, what I'm going to do is to have a look at the bus controller state machine, because this is one that I've already converted mostly. So we're going to be looking at that one from where it appears in the PDF document and converting that and actually programming one of the PLD chips and then even testing it. This is the internal design document, and this is 161 pages. This is page 38, where the bus controller state machine logic goes. And you can see here there are 2 versions of these documents. One is more for photo mode, so it's optimized for probably printing out and being viewed, and the other one was optimized for text mode. So I generally use the text mode ones for copying text. Occasionally it's easier to actually get the text out of the photo mode for one reason or another. But you'll see here that the definition here from July 1986, we've got the list of the pins, we've got the rules for each of the output pins. Now, one of the things to note here, where we have the colon equals, this means that this is a register. So this is using the clock, and it's actually using sort of a register or latch here. And then also down the bottom, you can see that there's a list of the tests to do, and then there's a columns for each of these tests at the top here. And there's a table with various values here. So whether or not things are clock, low or high input, low or high output, or high impedance, or I think in some cases there may be an X if we're not interested, and then a little description. So what I've done, I've already converted all of these into text files. So these are all being converted into text files, and I will make these available on GitHub in a couple of weeks when I've finished converting them into the other formats. So this is the example of the bus controller state machine. So you can see this is now being converted into a PALASM text file. So PALASM was the language that was used in the early sort of program or logic devices when they're sort of GALs and before they really became the more sophisticated devices in recent times. And you can see here that basically it's all come through fairly cleanly. It's required a bit of editing to correct. And this table here probably is the thing that requires the most work. And then you see we've also got the description down the bottom here. So this is the PALASM form. Now, to convert from PALASM into WinCUPL that we use for modern devices is relatively straightforward. I'll summarize the steps in a minute, but this is an example. So you see here I've put some standard header stuff that we need in here. We're actually going to be using a ATF22V10, although the original was a 20V8. In fact, the two chips are very similar, the only difference being the GAL20V10, then this pin and this pin were input only, whereas in the ATF22V10, then these can be inputs or outputs, but it basically is still a 24-pin chip. And in converting it, we need to define the pins for the individual definitions, and in PALASM, if you have a slash in front, then it's a negative, it's an exclamation mark in WinCUPL. Got the outputs. And you can see here where we had the colon equals, then we've now got the D latch terms. And you'll also notice that the syntax has been changed. So we've got ampersands rather than asterisks, and we've got hash signs, pound signs rather than pluses. And we also need to specify the output enable terms, which I think were done implicitly. And I haven't included the test rules here, and I'll show you the reason for that in a minute. So if we actually go into WinCUPL, we can actually compile that. If we compile this, compile successfully. If we have a look in the doc output file, this shows us all the rules and also gives us a pin output diagram here. So it's always a good idea to check this against the pin out in the PLD file just to make sure everything's coming out as expected. And if we have a look at the GED file, this is the file which is used to send to the programmer to program the chip. You'll see that there's all of the definitions for the fuses here, but it only goes down probably about just over 1 page worth here. And we'll come back to this file in a minute once we've looked at the simulation. So those rules that I showed you at the bottom of the file here, if we convert those into a simulation file, we specify the order of the fields and we'll then specify what the individual tests are. Now we have to do some conversion here. So unfortunately with the XGPro, then we do need to change the highs and lows for inputs to be ones and zeros, and there's a few other conversions we need to do. So if we just have a look at that. So we're using the Compaq DeskPro tech spec, and I'll include the URL in the description below. So in converting from PALASM to CUPL, you can see we've assigned the pins to pin numbers. We've converted the slash pin name to exclamation mark. Where we had the colon equals, then we've changed that to a .d register, and pin 1 would then be used as a clock. And there are certain of the PLD definitions have these if conditions which don't have a direct equivalent in CUPL. So if we had a if/test B0 clock is equal to the following, that is actually, that test condition needs to be combined with every single term in here. So it's a bit more cumbersome, but it's not too difficult to actually convert. As I said earlier, the asterisk maps to an and the plus maps to a hash, as you can see here. So this is a simulation file that I've already shown you. If we now hit simulate, this will now try and test out the rules against those conditions that we included at the bottom. And you can see here, these are the output files, so these are the various rules and things it's used. And then the simulation output. If there were problems with the rules or the pin definitions and things, then we would actually get error reports in here, and it would also show any of the particular tests. So we've got 54 tests here. If any of those tests were failing, it would actually show us. Now, in fact, there were 2 tests that were actually failing. I did have to make 2 alterations. So if you actually look here, you can see that vector 25 and 37, TS0 was changed from low to high. So I suspect either it's a problem with the original file or that there might be something else going on here. That's something we need to be aware of. Basically, the TS0 term, this one here, needed to be changed for the rules to actually work. So when we're looking at this one, I'll go into a bit more detail, check if that is actually correct or not. We might have made a mistake in some of the logic rules in converting them. But now that we've generated the simulation, we can see the simulation has passed and all the rules have passed. If you look at the GED file, what it's actually done is actually added on the test rules at the end. Now, it just so happens that those test rules are in a format which are actually fairly straightforward to convert into a format that our EPROM programmer can actually understand. So this is the XGPro program I use, the T56 programmer. You can also use the T48. And it includes a test facility. And if I show you one of the tests I did for the PLD I used in the earlier videos, you can see here this is the Gates 386, which has a couple of things for the byte enable decoding that I was looking at. You can see here that we've got V for the +5, G for the ground, 0 and 1 for inputs, X is for outputs we don't care about, and if we look at one which has some tests, you can see we've got high and low for outputs. So we need to basically make sure that the rules are actually in this type of format. And it just so happens that if we convert the input L's to 0 and the highs to 1, make a few other changes, so changing the X to N, and then once we actually get that GED file output, we can actually copy the GED file vectors into a YAML format file. And the reason for this YAML file is there's this utility down here called XGPro logic, and this will actually convert inputs in various file formats into the XGPro test import format. So in fact, what we can do is by doing a few simple edits, sort of replaces really on the output from our GED file, then we can actually feed it into this utility and it will generate us an LGC file which is used to import those rules into XGPro. So let's just show you what that involves. So what we do is we take the GED file output that I showed you, we copy it into this YAML file. So it's again just basically a dash at the beginning of each one with the conversions I said about the V's and the G's that we needed to make. Then in Windows Subsystem for Linux, we've installed this XGPro logic utility. Again, I'll include the URL for that in the description below. We run that and that will actually have generated an LGC file. And then when we go into our XGPro programmer, we can actually go into the import option here. And in fact, you'll see that there is a LGC file being created just now, this thing. Now, I've already got this imported. So if you actually look at the one that we've got here, and that has now brought in all of the rules. You can see we've got the definitions and we've got 54 rules here. So this is really going to be a massive time saver. So hopefully this will mean I'll be able to test all of these PLDs that are actually doing what the original tests were defined for in the original Compaq DeskPro. So what I'm going to do first of all is I'm actually going to just program this chip. So I've got an ATF22V10C in my programmer here. So we'll just read it just to make sure it's in correctly. We're going to read our GED file, D4-STATB, program it. Okay, so we've programmed it, but we don't know if it's working. Now, if we go into our test utility here, choose our ATF22V10 D4-STATB and test. So in fact, we can now verify that this is actually working. Apart from those two minor changes I need to make on the TS0 there, then that's really basically taken the output from here and put it into configuration files we can actually use to program the PLDs. So I've already done that for this one here. So I've already converted some of these other ones in orange into the CUPL format, but we also need to do all of the tests and things as well. So it's going to take me probably another week or so to go through and do all of these and actually start laying out the board. But I just wanted to show you what progress I was making, and it's quite complicated to work out how to do all this sort of stuff. And one other thing I've also just about completed now is I have actually been working on a KiCad version of the diagrams that I've been showing you. So this is the CPU one. And the reason why I'm doing this is that it just makes it a lot easier to actually track down what's going on. So for example, if we're on a particular page, you want to know which pins we used where, we highlight the memory read control signal there. We can see that it appears on the ISA bus connector. It appears over here, coming into this PLD here. And it's also being used actually from the DMA coming back in. So it makes life a lot easier to work with. And you can also see there's actually an output here during the dynamic RAM refresh logic as well. So having the DeskPro 386 design actually in KiCad should actually make life a lot easier. And I will be copying sections of this over into my new Breadboard 386 version, in that there are certain sections here which will largely be copied across as they are. And in particular, when we're looking at these PLDs, so the PLDs around here, here and here, this will actually help to try and work out what on earth is going on. So I'm going to break the video here. So hopefully it's given you a feel for the challenges of getting this next stage of the project working. So once I've got all the program or logic devices converted and programmed, then we just need to lay out the breadboard so that we can actually hook up the 386 to a working PC. So if you don't want to miss out on future videos, please hit subscribe. And if you'd like to leave comments, I do try and get back to you within about 24 hours where I'm able to. If you found the content interesting, please hit like, just helps to make it available to more people on YouTube. Thanks to all those who have been clicking thumbs up. Thanks for watching.